Hello, in this video, I want to go over how to use Newton's method to find the zeros of a function. So let me jump right into it. So you're used to being able to find zeros of quadratic functions. So this would be hopefully an easy problem. If you were given that f of x is x squared minus 3x plus 1, and you set that equal to 0, and you wanted to find where f of x is 0, you would do the quadratic formula, x equals 3 plus or minus the square root of 9 minus 4 over 2. Hopefully you know where all of that comes from. And so the answer would be 3 plus the square root of 5 or 3 minus the square root of 5 over 2. All right, so that would give you two zeros because that's a parabola that would intersect the I believe it goes this way, okay, and it's going to have two different zeros when we look at it. Well, I believe one of those zeros is actually negative, unlike the picture I just drew. What's much harder is finding zeros of functions that aren't simply quadratic, okay? So the method for solving a cubic function is much more complicated than for solving a quadratic function when it's equal to 0. So finding the zeros of that is a more complicated business. And higher degrees would be even harder, and functions that aren't polynomials are even more difficult for finding zeros. But Newton came up with a good method for doing it. All right, and it's tied into linear approximations, which we just learned about. So Newton takes linear approximations of functions and uses it to find zeros. All right, so let's look at the function that we've been given. All right, so let me make a little chart here, okay, a t-table. And I have figured out some of these values in advance so that we don't have to waste too much time in the video. But I'm going to have x values that range from -3 up to 3. Just extend this line a little bit further. All right, and f of x at those values. So we simply plug those x values into the given function: -17, -1, 3, 1, -1, 3, and 19. All right, so Newton didn't have a TI-84. We can easily just stick this into our TI-84 and find the zeros of the function. All right, it has a lot of computational power that Newton didn't have. So if he was trying to find the zeros of that cubic function, he would have made a t-table like we did. And then he would probably have sort of plotted out what it may have looked like. So let me just plot out what that might look like over here. And we'll just put it in an x-axis like this. All right, and we're going to make tick marks in this direction exactly 1. So that's -3 to 3, but in the other direction, because the values get big, we're going to go by 5s instead of 1s. So this will be 20 up here, and 1, 2, 3, 4, and -20 down there. So if we were to quickly put in our points, it looks like, the first point, let me switch colors here. The first point would be about there. The second point would be about there. Third point would be about there. And then let's see, 0, 1. Okay, 1, -1, right about there. 2, 3, that's about there. And 3, 19 is up there, right? Now, if we kind of roughly sketch in what this graph looks like, Newton knew what cubic functions look like, so he would know there are no zeros beyond this region. And we also can see that if we look at this, we must have circled, had something that roughly looks like that. All right. But Newton wanted to be able to find where the zeros of this are very precisely. So let's mark on our graph where the zeros are. They're in green. There's a 0 right about there. And let me pencil in another one. There's another one right in there and one right in here. And we want a high precision answer, sort of like we could get up here for our quadratic formula. right? Now, Newton came up with a method that will give approximate answers, not exact answers, but they will be extremely precise, okay? So essentially what Newton is doing with his method is he's saying, let's find a place close to the zero on the function and do a linear approximation of it. Okay, we create a tangent line of the function, and then let's find where that linear function crosses the x-axis. And you can see that those two, where the linear function crosses the x-axis is extremely close to where the function itself crossed the x-axis. If we started with a point of tangency that was relatively close to the zero, right? So now let's work on the method in detail, and then we'll look at a Matlab simulation of what it is that we did, okay? So there are 3 zeros. The first, we can see in our t-table, whenever there's a sign change, there must have been a 0 in between. So between values of -1 and 3, there must have been a 0. So that corresponds to the region between x equals -2 and x equals -1. And it appears that, maybe it's a little closer to -2 than it is to -1, right? We can see that we have another sign change here. So there must be another 0 between x equals 0 and 1, which we could see on the graph to the right. And there's another 0 here between x equals 1 and 2, which we can also see on the graph on the right. And those zeros are somewhere in the middle of those regions. We just don't know exactly where. So for this video, we're going to focus first on the 0 that is to the far left, all right? And a reasonable first guess is to guess that A is -2. So that's sort of our first guess of where the 0 is. We know it's not quite right. We probably could make it a little smaller and get closer right away, but I want you to see how the method works, okay? So we're going to do a linear approximation of f of x near A equals -2, right? So the first thing we need to do is we already know that f of -2 from the t-table up above is -1. So now we need to find f prime of x, all right? And given that f of x was this cubic function, the derivative is 3x squared minus 3. The derivative evaluated at -2 is just equal to 9. Okay, so it's very steep slope right there at x equals -2. So continuing, let's try to find a linear approximation of the function. So hopefully you remember that a linear approximation near -2 would be the f of -2 value plus f prime of -2 times x minus -2, which is x plus 2. All right. So we can put in our numbers and we can say, oh, the linear approximation in this case will be -1 plus 9 times x minus 2. And doing a little bit of algebra, that comes out to 9x plus 17, right? Now, to find the 0 of the tangent line, all we have to do, let's switch over colors here. We're going to set L of x equal to 0. So we want to find out where 9x plus 17 is 0. And with just a little bit of algebra, you can see that's 17/9. All right. Which, if we do it as a decimal approximation, is about -1.8889. Right? Now, let's see how close this answer actually is. So I've written in Matlab code that actually follows the algorithm we just used, and we can visualize what would happen. Remember, Newton would not have had code like this, so but he could visualize in his head pretty well what was going on. So this code will help us to see what Newton's method does. So if I run the code, if I need to dock this figure so you can see it, so a graph figure just popped up. Let me dock that. Okay, and you can see it there. So the tangent line, the point of tangency is right over here where I have the cursor now, all right? And you can see that the zero of the tangent line is plotted with a little red circle. And it looks like that is extremely close to where the zero of the blue line, which is the function, where that would be, right? Newton wouldn't have been able to see the whole function like we can because he didn't have a graphing tool like this. But now what I want to do is use the zoom tool and get a good idea of just how close that is. So we're going to box in this little region here. And you can see that the zero is just a little bit to the left of where it should have been, right? It's close. If we wanted it to the 10th, we already have an answer, right? But let's say we wanted an answer that's closer than the 10th. Okay, so you can see if we zoom in a couple of times, that's not exactly where we would want it to be. I think we can get closer. So the way we get closer is we do a second iteration, okay, where, remember, we started with a guess of -2 being the answer. Newton's method has now given us a better answer as a new starting point. So let's go back over to the iPad share. And here we go. It should be popping up any moment. There we go. So this has become a new guess. All right. So we're going to repeat the process. Our second guess, this is our second guess as opposed to our first guess. So this is going to be our second iteration of the process, is that A is -1.8889. Okay. So that means we need to find F of -1.8889. All right, or we could have used -17/9. Newton probably would have done that. And we end up with a value of -0.0728. Then we found the derivative function already. Okay, we know it's 3x squared minus 3. So if we evaluate that at -1.8889, we end up with 7.7038. Okay, so this gives us a new linear approximation. Okay, this linear approximation is -0.0728 plus 7.7038, the new slope, times x plus 1.8889, because this was the new a value. Okay, so remember, this is the new a. So we're doing all of this at the new a value, right? Then the next step would be to set all of this equal to 0. So 0 equals -0.0728. I'm just going to copy quickly. And I have solved this in advance, all right, and found that x was -1.8795. Okay, so notice that changed slightly. Look at the answers that we have. This is a new answer compared to the first answer. So this was after the first iteration. And this is after the second iteration. So it didn't change drastically, but it did change significantly. Okay, in the 100th place, we have a different digit now. So let's go back over to Matlab and see what that looks like. Okay, so in Matlab, this would be, we have our first iteration here, which we already had. Let's see what happens when we go to 2 iterations of the process. Okay, you can see the tangent line shifted slightly as we changed our point of tangency, and then it gave us a new 0. And let's zoom in and see what that looks like. Well, it looks close from here, but if we zoom in, it's still very close. And we could zoom in on the zoom. And you can see in 2 zooms, it's still extremely close. We go in another box, it's still close. So this is extremely close. One more zoom. Finally, after 4 zooms, we can see a difference between the 0 from the tangent line approximation, the second tangent line that is, and the 0 of the function, right? So let's just reset that. Let's see what happens if we were to do more iterations. Like, did we get close enough? It really depends on how much precision we want. Okay, so if I do one more iteration, 3 instead of 4, you can see that the digit at the 10,000ths place changed. So if we only needed to be precise to the thousandths place, 2 iterations would have been enough. 3 was overkill. And if we do another iteration, you'll see that it doesn't even change at the 10,000ths place. So we do get closer to the 0 every time, but it may not be significantly better once we apply the method more than a couple of times. So in this case, 2 iterations, we had a pretty good starting guess of a equals -2. And after 2 iterations, we really closed in on where the 0 would be, right? Now I want to spend a little bit of time showing you when, how Newton's method could fail, all right? So we have another 0. I'm going to show you how it works again. We have another 0 in here somewhere between x equals 0 and x equals 1. Perhaps Newton would have guessed that that was at 0.5, or he probably would have said 1/2. All right. Did that get us close in one iteration? It looks like it got us close. So Newton's method was very good in one iteration because half was a pretty good first guess. Oh, I'm sorry. The reason that was so good is because I was doing 4 iterations. Let's see if it did well in one iteration. So if we zoom in, it's off slightly, right? If we go back and do it in 2 iterations, I believe it will be just like our first answer. I think it will be extremely good after 2 iterations. So 1 zoom, 2 zooms, it's still very good. So the first guess was good enough and it got us there very quickly. But what would happen if we had guessed that our 0 was at 1? Okay, we can't just randomly make guesses, because look at what happens if I guess that a was 1. Whoops, what happened here? I'm not seeing my tangent line at all, okay? And part of that, the reason for that is because at a equals 1 exactly, the tangent line would be horizontal, because that actually turns out to be a local minimum of the function. Not sure why it's not graphing it in, but it's not. Let's see if we went a little bit to the left of that, to 0.9, and let's see what happens. Oh, I know we were at 2 iterations. That's the problem. So let's go back to a equals 1 and do 1 iteration. Okay, we can see a constant line because a equals 1 is right at a local minimum. So it wouldn't do a second iteration because it didn't know where to start the second guess, because we never had a 0 for that tangent line. So if we change this down to, well, keep this at 1 iteration, but change the a value down to 0.9, let's see what happens. Now we do get a 0, but there's a problem with this second 0. Okay, so we guessed that the 0.9 was where the 0 would be, but it tells us using Newton's method that it is over here at about -0.9. There's a problem with that. That's not very close to the 0 we're trying to find. So what's going to happen is we'll get another tangent line starting at around, well, actually, you can see up here at the top, the number is -0.8. Okay, so if we do 2 iterations of it, the second tangent line started around -0.8, and notice where its x-intercept is. Okay, it's all the way over here at close to 1.9, which is on the, not only is it not near the 0 we're trying to find, it's actually closer to the 0 over here to the right. All right, and if we do another iteration, we'll actually close in on the wrong 0. All right, so you can see how after 3 iterations, it's getting very close to the rightmost 0 of this function, which isn't the one we wanted to find, right? So if we don't start close enough to the point that we're interested in, we can actually end up, the tangent lines may have intercepts that aren't anywhere close to the intercept that we're trying to find. So you do need to be careful. Your first guess needs to be reasonably good. You want the guess to be on a section of the function that's relatively linear compared to the function as it crosses a 0 in order to quickly get to an answer, right? You don't want to have to use Newton's method more than a couple of times because it's time consuming and tedious. So a good first guess is really important. A bad first guess can actually lead to wrong answers. So do be careful when using Newton's method.